In this lecture, we will analyze the receive antenna diversity system. As we talked about the receive antenna diversity in the previous lecture, the input-output model in vectorial form is given by y bar is equal to h bar into x plus n bar. Now, the variance of noise is given by expected value of the norm of Nia square. We will see how the signal is detected from multiple receive antennas. The signal we receive multiple copies of the signal at the L receive antennas given by Y1, Y2 to YL. The question here arises how to combine or collect these received signals. One method of combining these received signals is to scale each of the received signals by some vector W1 to WL. So the combined received signal would be given by W1 conjugate multiplied by Y1 plus W2 conjugate times Y2 plus WL conjugate times YL. If we write this in vectorial form, we would have a row vector of WL conjugates multiplied with a column vector of Y bar. Combined vectorial form, it is given by W bar Hermitian times Y bar. This W bar vector is called a beamformer, or this whole system of multiplication of beamformer with the received signal vector is called beamforming. So what effectively we are doing is that we are forming a beam in the direction of the received signal. The beam is given by W bar, and W bar Hermitian is given by the conjugate transpose of these values ranging from W1 to WL. We use W notation because we are performing beam or beam forming, which is given by weight vectors. So we need to analyze the now received signal to noise ratio with the help of these vector or vector model y hat is equal to h at x plus n bar. So the beamformer output. Now the beamformer output can be given by y bar Hermitian into h bar x plus n bar. We just replace the value of y bar here as hx plus n. So if we open the brackets, we have y bar Hermitian h bar x plus w bar Hermitian n bar. This is the signal component and this is the noise component. From these signal component, we can calculate the received signal power, and from this combined noise component we can find the combined noise power in terms of beamforming vectors. So SNR is given by signal power to the noise power. The signal is given by this. The signal power is given by norm of W bar Hermitian H bar square multiplied with signal power. Now we can separately calculate the noise power. Noise power has some interesting characteristics. As studied before, noise power is given by the expected value of W bar Hermitian N bar square. So if we open these brackets, we have W bar Hermitian N bar multiplied with W bar Hermitian N bar conjugate. So we have two different terms, W1 conjugate N1 plus W2 conjugate N2 plus WL conjugate NL multiplied with W1 N1 conjugate plus W2 N2 conjugate plus WL N1 conjugate. This terms comes from the value defined here. So this whole multiplication can be written in terms of elegant compact equation. So if we take the expected value of this whole equation, we see that the unlike terms with indices I and j which are not equal, this whole term turns out to be 0. The reason behind is that the noise is independently drawn at different antenna elements. So there is no correlation between the noise at independent antennas, and the expected value of Ni into Nj conjugate would be equal to 0. So the only terms are remaining the noise power at each independent antennas I. So the noise power is given by the expected value of sum of Wi square into Ni square. So we can rearrange the terms. We can take out the summation outside and the expected inside. So only random variable is Ni. The expected value of Ni square is basically sigma n square. Finally, the noise power is given by the sigma n square times sum of Wi square. Sum of Wi square is a Frobenius norm square. So finally the noise power is sigma n square into W bar norm of square, or the square of norm, given by sigma n square into W bar Hermitian into W bar. So noise power at the output of the beamformer is given by this equation, where W bar is the beamformer. Finally the SNR at the output of the beamformer is given by W bar Hermitian into H bar square into P divided by sigma n square into W bar Hermitian into W bar. We can skip the values of this noise as they are redundant. We can calculate the expected value of noise. Now, how to choose a beamforming vector W bar? We need to choose W bar such that W bar maximizes the SNR. So the equation becomes like this. SNR is equal to some constant value K into W bar, which gives the same value as the SNR. We need to choose W bar such that W norm Frobenius norm square is equal to 1, which gives W bar Hermitian into W bar equal to 1. That means the SNR would be equal to W bar Hermitian into H bar square into P divided by sigma n square, such that W bar hat norm is equal to 1. So W bar is equal to some constant C multiplied by H bar, where C square H bar's norm square is equal to 1, so C is equal to 1 over H. This can be seen with the simple equation. A bar permission into B is actually A bar into B bar multiplied by cos of theta. When theta is equal to 0, we get the maximum value of A dot Hermitian into B bar. So optimal beamformer or optimal beamforming vector W is such that maximizes the received SNR. So received SNR can be maximized if we choose the weight vector W or the beam factor W is equal to H bar divided by H bar norm. So SNR is given by W bar Hermitian into H bar absolute value square into P divided by sigma n square. Now maximum SNR can be achieved if W bar as calculated before is given by H Hermitian to H norm divided by H norm into H bar the square into P divided by sigma n square. So at that value, when W bar hat would be maximum, so SNR would also be maximum. So finally that maximum SNR would be given by norm of H square into P divided by sigma n square. So this is why this system is called maximum ratio combining. Maximum ratio combiner gives an optimal beam factor W bar that maximizes the received SNR. This is also called a spatial matching filter. An example is given here for L is equal to 2 receive antenna systems. Y1 and Y2 would be the received copies of one same transmitted symbol X through links L1 and L2. The input-output equation in vectorial form is shown here. So if we put the values of the beam-forming vectors, so for example we have H1, a complex number given by 1 over square root of 2 plus 1 over square root of 2 j. So mod of H1 would be given by square root of 1 over 2 plus 1 over 2, or the absolute value of H1 would be given by 1. Similarly, absolute value of H2 is given by 1, where H2 is equal to 1 over square root of 2 minus 1 over square root of 2j. So the combined vector H is given by this vector. Norm of square of H bar will be given by 1 plus 1 is equal to 2. So this means H norm of square is equal to 2, H is under root 2. The weight vector for maximum ratio combining is given by H bar over H square, or for Venus norm it is given by this value 1 over 2 plus 1 over 2j and 1 over 2 minus 1 over 2j. So output of the received beamformer will be given by W Hermitian to Y bar, W bar Hermitian to Y bar. If we multiply these values, we get this whole value, which is the output of the beamformer. Thank you.